Well, the fine-tuning of the laws and the constants of physics and the initial conditions, that is the arrangement of matter at the beginning of the universe, is one of the most extraordinary discoveries of the 20th century in physics. It started in the 1950s with a man named Fred Hoyle, a prominent British astrophysicist, now Sir Fred Hoyle. And Hoyle discovered that the conditions that were necessary to make it possible for carbon to form in the universe were incredibly improbable, and there were many conditions that had to combine to make it possible for lighter elements, in particular beryllium and helium, to combine to make carbon. It also was apparent to Hoyle and many other scientists that we need carbon because carbon is a molecule that allows long chain-like molecules to form, and it's necessary for storing information, which is a critical condition for life. All life is carbon-based. People have speculated about life being silicon-based or something else, but Hoyle and other physicists who knew the score knew that that wasn't a serious proposal. And so it absolutely shocked Hoyle when he discovered how many different parameters had to be just as they are in order for carbon to form. Carbon forms in the center of stars through a process known as nuclear synthesis. If the gravitation inside stars is too weak, then the temperature of the star won't get hot enough so that the beryllium and the helium will combine to form carbon, beryllium and helium being lighter elements. If the gravitation is too strong, however, the star will simply burn up before those critical reactions can take place. And that was only one of a whole suite of exquisitely finely tuned conditions that had to be just right. And when they did the mathematics on this, when they calculated how finely tuned these parameters were, they were getting numbers that were 1 in 10 to the big exponential numbers in each case. So it's a kind of a concept like in engineering of tolerances. Things have to be within very narrow bounds in order for things to work. So in order to get a life-friendly universe, we're kind of in what you might call a Goldilocks zone, where multiple parameters, now we know about 36 of these, the expansion rate of the universe, the strength of gravitational attraction, the ratio of fundamental forces like the electromagnetic force and the strong nuclear force, all of these, the strength of these forces have to be just right to allow for life to exist in building carbon, having stable planets and galaxies. Many, many conditions of life depend on these fine-tuning parameters being just right. And so you can think of it as a Goldilocks universe. Not too hot, not too cold, the force is not too strong, not too weak, speed of light not too fast, not too slow, expansion rate of the universe not too rapid, not too... So things are just right. And this has caused many physicists, Hoyle in particular, to shift their perspective on the big worldview questions. Hoyle was an atheist who resisted the discovery of the Big Bang because he thought it implied a creation event, came up with an alternative theory that was later refuted called the steady state theory, but then after the fine-tuning realized that there must be some design behind the universe. And he said a common sense interpretation of the data suggests that a super intellect has monkeyed with physics and chemistry to make life possible. So that's what the fine-tuning is about. It's a powerful evidence of design that's come out of physics. The evidence of the exquisite fine-tuning of the laws, the constants, and the initial conditions of the universe have suggested to many physicists that the universe is a setup job, that it was finely tuned because there was a fine-tuner who chose the parameters. A popular alternative explanation for the fine-tuning is the idea of the multiverse. The multiverse acknowledges that the conditions necessary to make life in this universe are incredibly improbable. But it posits the existence of multiple billions of other universes that would, in toto, make the conditions necessary for life likely somewhere. And then there's the additional assertion that, well, we just happen to be in that lucky universe. And so the multiverse tries to expand what are sometimes called the probabilistic resources. If just one universe isn't enough to render the incredible fine-tuning probable, well then let's posit a whole bunch of others so that at some point the conditions just must have had to have arisen. Now, in order to make that explanation work, multiverse advocates realize that there needs to be some connection between these different universes. If all the other universes out there have no connection to our universe, then whatever happens in those other universes doesn't affect the probabilities in our universe. So in order to portray these multiverses as the kind of outcome of a cosmic lottery, multiverse advocates have realized they needed to posit some kind of universe-generating mechanism that would, in a way, provide a common causal connection between all of them. All of the universes have sprung from the same mechanism, and then we can think of our universe as just one of many outcomes of a kind of lottery. Now, and this is where the problem comes in for the multiverse, because it turns out that every mechanism that's been proposed, whether something out of a cosmology called inflationary cosmology or a mechanism from what's called the string theoretic landscape, every mechanism that's been proposed to explain where these new universes come from has itself required prior fine-tuning. Theoretically, you just don't get this great variety of other universes unless there's something fine-tuning the mechanism. So the upshot of this is that the multiverse explains the fine-tuning only by reference to invoking prior unexplained fine-tuning, and so in the end you're left right where you started. You haven't really explained the fine-tuning that makes life possible in our universe, or for that matter, anywhere else. One alternative explanation for the fine-tuning of the laws and constants and initial conditions of the universe is the idea known as the weak anthropic principle. According to the weak anthropic principle, we shouldn't be surprised to find that we live in a universe that has conditions which are conducive to our existence. After all, we're here. And since we shouldn't be surprised by the discovery that we live in a universe that has conditions that are conducive to our existence, there's nothing to be explained. No surprise, no need for an explanation. Now, the problem with this alternative explanation is that it really fails to reckon with the thing that really does surprise us, and which is really does need explanation, and that is the incredible improbability of the conditions that are necessary for our existence. We shouldn't be surprised to discover that there are conditions that are conducive to our existence because, after all, we're here. But we can be very surprised to discover that those necessary conditions of our existence are so incredibly improbable. Here's an illustration that gets this across. It's from the philosopher of science John Leslie. Imagine you're standing before a firing squad of trained Nazi marksmen, and they've found that you've been caught in a plot to kill Hitler or something. Anyway, the order comes, ready, aim, fire, and suddenly there's a barrage of bullets, and you are behind your blindfold, but the noise stops, and you discover you're still alive. And then you turn around, take the blindfold off, and there's a pattern of bullets that circumscribes your body, but none of them hit you. Now he says, of course, says Leslie, you should. What should you think in that place? Well, of course, he says, you shouldn't be surprised to find that you live in a universe that has conditions that are consistent with your existence. But you should be surprised that you're still alive because those conditions are so improbable in relation to what you know about the skill of the marksman and how many of them there were firing at you. So the weak anthropic principle doesn't really explain what needs to be explained, which is not just conditions that are consistent with our existence. It needs to explain the improbability of those conditions, and that it fails to do. Another problem with the weak anthropic principle idea is that it confuses a necessary condition with a causal explanation. In particular, our need for a causal explanation of the incredibly finely tuned and improbable conditions that are necessary for our existence. To illustrate, imagine there's a fire in your city, and the insurance company sends out an investigator to find out what caused the fire to occur. The investigator goes out and he sees, well, there's some matches, there's some old gas cans, there's some little sprinkles of extra gas on, and a lot of charred buildings. But he doesn't really take any note of that. Instead, he comes back and he files his report and he tells the insurance company, well, I know what caused the building to burn down. It was the oxygen in the atmosphere. They say, what? Oxygen? Yes, oxygen, he says, is a necessary condition of fire. You can't have a fire without oxygen. Well, what's his mistake? Well, he's confused a necessary condition with a cause or a sufficient condition or a set of sufficient conditions. And really the cause was, in this case, arson, and he overlooked all the clues. Well, this is effectively what the weak anthropic principle does. It says, well, here's we are citing a necessary condition of our existence, all these fine-tuning parameters. What more do we need to explain why we're here? Well, what we really want to know is not just what the conditions are. We want to know, and whether they're necessary or not, we want to know what caused those conditions to come into existence that would explain jointly why life is present. And that the weak anthropic principle doesn't do. What we need to know instead is a causal explanation. Design provides that explanation because it tells you why the conditions were set and why they're so incredibly improbable. The weak anthropic principle doesn't. One of the great discoveries of the 20th century that has challenged materialism as a philosophy at a fundamental level is the discovery that the universe had a definite beginning. In fact, the material universe is now thought to have had a definite beginning, that if you go back far enough in time, the curvature of space becomes infinitely tight, corresponding to zero spatial volume. That's a consequence of a theorem known as the singularity theorem that Stephen Hawking and Roger Penrose proved in 1968. It was a consequence of their solving Einstein's gravitational field equations, reflecting his theory of general relativity. So this is a mind-blowing conclusion in modern cosmology. There was first the discovery that the universe is expanding outward in every direction of space because of the red-shifted light coming from distant galaxies, and then theoretical considerations from general relativity also reinforce that idea, showing that the universe, the material universe itself, had a definite beginning. Even time and space began. If there's an infinitely tight curvature of space, that suggests that there's no place to put any matter, and so you have a fundamental challenge to the materialistic worldview or the worldview of scientific materialism. Now, beginning in the 1980s, late 80s, Stephen Hawking and other theoretical physicists, Hawking, who was involved in the 1968 proof of the singularity theorem, didn't like that conclusion too much, began to think of some other alternative explanations. And Hawking came up with something called quantum cosmology, which he popularized in a book called The Brief History of Time, which he published in 1988. I was a PhD student at Cambridge at the time, and actually attended the series of lectures that Hawking gave that became the little book, The Brief History of Time. Anyway, since the late 80s, there's been this idea that the laws of physics by themselves can explain the origin of the universe from literally nothing, and that therefore there's no need for any kind of external agent or creator, no transcendent cause of any kind, that the laws of physics alone explain where the universe came from. So whereas in the early 80s, there were books coming out like God and the Astronomers by Robert Jastrow, and other major figures in astronomy were saying, hey, look, this Big Bang theory, this singularity theorem clearly has theistic implications. It's pointing to the need for a cause that transcends matter, space, time, and energy. Who does that sound like? But after the 1980s, this quantum cosmology idea has caught on and has seemed to kind of neutralize the implications of the Big Bang, at least with respect to being affirmative of theistic belief. In fact, many of the new atheists have taken up quantum cosmology as their go-to explanation for how you get a universe without God, one of those being Lawrence Krauss. Now, I've gotten more into quantum cosmology in the last couple of years, and it turns out there are a couple reasons to doubt that this idea of invoking the laws of physics, the laws of quantum physics, can explain where the universe came from in the first place. The first is that this whole research program misunderstands what laws do. Laws don't explain where matter and energy come from. Laws describe how matter and energy interact once they exist. They don't give you an origins explanation. They describe the ongoing behavior of the entities within the universe. So that's a fundamental philosophical problem. Secondly, a law of physics is expressed mathematically as an equation. And those equations exist in the minds of mathematicians and physicists. They don't actually exist in nature. Our laws describe the behavior of material entities and energy and so forth, but they don't in any way cause things to happen in the material world. So to say that the laws of quantum mechanics cause the universe to come into existence is a strange kind of category error. It's like saying the latitude and longitude lines on a map are responsible for the rise of the Himalayan mountains. The map describes where the mountain is, but it doesn't tell you how the mountain got here. Now, there's one final problem, and this is the one that I think is most profound. The quantum cosmological model wants to describe our universe as a reasonably probable outcome of something called a quantum mechanical wave function. It's often represented with the Greek letter psi. So psi is a function that describes all the possible gravitational fields that could be instantiated or exemplified by our universe. Gravity, in Einstein's view, is curved space as a result of the concentration of matter. So this universal wave function describes all the different configurations of matter and all the different shapes of space that the universe could have. And it becomes an origins explanation when that wave function includes our universe as one of the reasonably probable outcomes of all those possibilities. But here's the problem that I discovered. In order to get a quantum mechanical wave function, you have to solve a prior quantum mechanical equation, something that's analogous to the Schrödinger equation in ordinary quantum mechanics. But the physicists themselves tell us that you can't solve that equation unless you apply a number of what are called boundary constraints, which are limitations on the mathematical degrees of freedom expressed in that equation. Or another way to put it is the equation is insoluble without the imposition of boundary constraints. But who imposes the boundary constraints? Who restricts the degrees of mathematical freedom, the possibilities that could exist? Well, it's the theoretical physicist. Now, anytime, and this is basic information theory, anytime we say we exclude one option and elect another, we're imparting a bit of information. So if there are an infinite number of solutions to this prior equation, and that's what the physicists tell us, then you have to supply a huge number of boundary constraints to make the equation soluble, and that means you have to supply a huge amount of information. And in the mathematical modeling of the origin of the universe, who supplies that information? The theoretical physicist, the intelligent agent. So even in cosmology, it now appears that there's an information problem that's only solved in our modeling by an intelligent agent choosing some boundary restrictions, boundary constraints, and limiting the mathematical degrees of freedom in various ways to generate a wave function that includes our universe as a reasonably probable outcome. So you've got multiple problems with this quantum cosmology, but the deepest one is that it's actually modeling the need for information to give you a finely tuned universe.